Hi friends. Today I am going to tell you about white holes. If you not subscribed our channel yet, then please subscribe it. Let's start. A white hole is a hypothetical feature of the universe. It is considered the opposite of a black hole. As black holes don't let anything escape from their surface, white holes are eruptions of matter and energy, and nothing can get inside them. White holes are a possible solution to the laws of general relativity. This law implies that if eternal black holes exist in the universe, then a white hole should also exist. It is a time reversal of a black hole. They are expected to have gravity, so they attract objects, but anything on a collision course with a white hole would never reach it. Theoretically, if you were to approach a white hole in a spacecraft, you would be inundated by a colossal amount of energy, which would most likely destroy your ship. Even if your spaceship could withstand gamma rays, light itself would start slowing you down like air resistance slowing down a moving vehicle on Earth. And even if the spaceship is built to be unaffected by the energy emission, space-time would be weirdly warped around a white hole. Approaching a white hole would be like going uphill. The acceleration required would get higher and higher while you move less and less. There isn't enough energy in the universe to get you inside. Of course, this is fairly counterintuitive. How could energy in the white hole seemingly come from nowhere other than space-time itself? This is one reason why their existence is very unlikely. However, there are some theories in which white holes are possible, but perhaps not quite as described in general relativity. As they are alleged counterparts of black holes, white holes too would be formed by a gravitational singularity. A singularity is a point-like feature in spacetime where the gravitational field becomes infinite. Infinite values in physics are usually an indication of missing pieces in a theory, so it is not surprising that quantum mechanics and relativity struggled to explain the finer details of singularities. Potential candidates. A lot of phenomena have been put forward as white holes. They are usually chosen because they are mysterious objects that we have not been able to explain in detail. Gamma-ray bursts, fast-spinning pulsars, and black holes reaching the end of their lives have all been considered. Even the Big Bang has been described as a white hole. But so far, no white holes have ever been directly observed, and even their theoretical existence raises some red flags. It seems like white holes are used as a place mark until more observations or a better theory come along. The Big Bang as a white hole is a clear example of this trend. Until we were uncertain about the size of the universe, there was speculation that the cosmos was produced by a white hole larger than what we could see. We now know that the universe is most likely infinite, which makes the white hole explanation almost certainly wrong. Theoretical constraints. A white hole is a particular kind of singularity, a naked singularity. Singularities like black holes cannot be directly observed, because the escape velocity, the speed you need to break free of its gravity, is greater than the speed of light, so nothing can escape from it. The singularity is protected by an event horizon, the surface that separates us from the black hole. Mathematically, when we have a singularity, space-time is broken. To avoid this issue, event horizons were introduced. A naked singularity has no event horizon. According to the fundamental principles of general relativity, the universe doesn't allow naked singularities. The idea is aptly called the cosmic censorship hypothesis. Numerical simulations and the current theories of quantum gravity, however, hint at the possibility of naked singularities. A curious phenomenon happens in describing a black hole's properties with a quantum mechanical approach, which doesn't include gravity. If you look at a black hole backward or forward in time, it behaves exactly in the same way and remains a black hole. This is not the most important clash between quantum theories and relativity, but it is significant nevertheless. The most important constraint is entropy, the measure of the order of a system. According to the laws of thermodynamics, the net entropy of the universe is always increasing. Entropy could decrease locally. For example, a freezer decreases the entropy of water by turning it into ice. But the freezer engines emit a lot of heat, so the total entropy is still increasing. White holes decrease entropy, which is a fundamental piece of evidence against them. In this universe, we obey the laws of thermodynamics. And so far, no confirmed violations have been observed, although we often hear claims of perpetual motion machines and unusual events. The future of white holes. White holes fascinate a lot of people and they give us a sense of balance. People will and should continue to study them. Indeed, several features of general relativity, black holes for example, were at first considered a theoretical curiosity. There is no hard evidence proving that white holes exist, but maybe in our vast complicated universe, there's space even for them. Thanks for watching. Please support us by liking, subscribing and sharing.